Hailing for power engineers, today's presenters offer more than 90 years of combined packaging experience. Calvin Blake is a 40-plus year industry veteran with specialties in beer, food, and PET. His career path, which has ranged from engineer to vice president, includes work with several leading packaging companies, including one working with major brands to design and install systems across Europe and Central and South America. Many line design concepts used today are a direct result of Calvin's instrumental development. Joining Calvin is Jim Stahlman. Jim's own 40-plus year career has included work for multiple major conveyor and equipment manufacturers. Starting as a conveyor designer, he's since taken on roles as a systems application engineer, project manager, regional sales manager, and international business unit manager. His system designs have seen successful applications in container manufacturing, canning, frozen food, light industrial, automotive, and, of course, beverages. To start off Bottling 101, what's the most unbelievable system design flaw you've seen in a plant?
Jim, we've been doing this a long time, and there are lots of stories. But the one that comes to my mind is years ago, we're invited into a pet food plant where they were running dog biscuits. And they chose somehow to run dog biscuits on air conveyor. And guess what happens on air conveyor? Dog biscuits run at warp speed. And at the end of the conveyor, what you end up with is a pile of dog biscuit crumbs and dog biscuits. What we did is we took a more conventional approach with a wide mat top conveyor, put splitter plates between the dog biscuits, and that way we could control the speed and population of the dog biscuits on the conveyor. Jim, I know you've got some stories.
Yeah, I've always got stories. One that relates to what we're going to talk about today. We had a client who purchased a depalletizer and a pressureless single filer from two separate suppliers. And at the beginning of the pandemic, suppliers couldn't travel. They'd installed the equipment, trying to get it running, and they'd spent 2 weeks trying to get the pressureless single filer running and could not get it running. I happened to be in the area on another project, and I went in, I watched it for like a minute, I asked for a 1/2-inch ratchet, and within 10 minutes we had it running well enough that they could start running their trials and tuning up the other parts of the line. And it's really just a matter of knowing how one of those things is supposed to work and what affects and causes issues with it. And we were able to help them out. So that was really a good story, I guess.
Well done, good story.
Yeah.
So what are we going to talk about today? We're going to look at, for a few minutes, at pressureless single filers that Jim was just talking about. We're going to look at rinser infeed and discharge. We're going to look at proper limit switch placement. We're going to look at accumulation models and design. We're going to look at a multi-packer infeed and a case packer infeed, and then packaging equipment accessibility, both for personnel and for fork trucks and for consumable materials. So let's take a quick look at the line that we've designed as our typical line to talk about today. Real quickly, we have our depalletizer, our pressureless single filer, lower rate of rinser, we have our filling and capping system. And since this is a beer line, we have a pasteurizer. Downstream from that, we have an accumulator, both a bidirectional and inline accumulator, pressureless single filer again for our labeling operation. And then we've segmented between our multi-packer and our case packer and onto our palletizer.
So we want to talk a little bit about VCurve theory. VCurve theory is setting up a critical machine on your line. In most cases, it's a filler, but there are other instances where it can be a different machine. The critical machine is kind of your bottleneck on the line, and it's a machine you want to keep running at maximum efficiency in order to be able to get the best efficiency out of your lines. In this case, we've drawn the beer line. The filler will be the critical machine set up at 650 bottles a minute. Upstream from that, we'll set the bottle rinser at 10% faster than the filler, 715 bottles a minute, and then we'll set the depalletizer 20% faster at 780 bottles a minute. The idea upstream of the critical machine is to store as much product as possible so that if there's a hiccup in the upstream machine, the critical machine keeps running, and once the problem is fixed, the bottles catch back up and keep that machine running 100% of the time if at all possible. Downstream from the machine, we basically do the same thing. The pasteurizer is going to be set up at 10% over, 715 bottles a minute. We set the labeler up at 15% over speed, which is 748 bottles a minute. Then we'll set up the case packer at 20% over the filler speed. That's 780 bottles a minute. And lastly, we set the case palletizer up at 30% over, 845 bottles a minute. What this gives you the ability to do is set up accumulators between these machines so that if a downstream machine goes down, we accumulate the containers, and then we absorb that accumulation back into the line as quickly as possible. Again, keeping that filler running 100% of the time if we can.
Well, let's go back to our line now and start with our pressureless single filer. And what we want to do here is talk about a typical design for a pressureless single filer. As we zoom into the pressureless single filer, I want to call attention to the parallel transfer just before the pressureless single filer. So many layouts that we've seen, Jim, do not include that transfer, and is so essential to proper line design. This transfer, known as a dosing conveyor or metering conveyor, allows you to create the correct population of bottles before entering the pressureless single filer. So it really needs to be there and is a very, very critical element. The next thing we see is the pressureless single filer itself, and basically broken into 3 zones. And the heavier the bottle, the lower center of gravity of the bottle, the guide rail can be a little bit more aggressive, which means that the combiner could be possibly a little bit shorter. But the thing we want to show here today is we have at least 2 motors on each zone of the pressureless single filer, because what is essential in the field is to be able to control the chains one against the other and create the proper line speed to separate the bottles and bring them along the rail. So many times companies will put 1 motor on each section, and it really makes it very difficult in the field to fine-tune the combiner and get the proper single file as you exit the combiner. Next downstream in this particular layout is a lower rate of rinser. These units have been around for many years and used in many applications. But one of the things, Jim, that we don't always see is a proper application of infeeding the lower rate of rinser. Here we've shown a parallel transfer immediately before the lower rate of rinser. And this is essential in allowing accumulation back upstream from the depalletizer and allow us once again to meter bottles into the lower rate of rinser. And this serves to do that. Using it properly with our controls, we can provide the proper gap of bottles going into the bubble grippers and around to the rinse section. Down below on the lower rate of rinser, one of the things we see many times, it's so simple to put in a relief table. The relief table is a small stainless steel table, usually 18 by 24 inches with a built-in limit switch. And this allows us to immediately stop the rinser on a backup or an e-stop so that the rinser does not continue running and push glass out into bottles that are already positioned below. It really becomes a glass crusher, rips up the bubble grippers, and creates a nightmare for plant operation people. So we really like to see this little table at the exit of the lower rate of rinser. We're going to move now downstream of the filler on the full side and talk just a little bit about bottle accumulation and a line flow pressure switch. In this particular drawing here, you will see us zoomed in on the backup switch on the mass bottle conveyor. You see the bottles populated on the conveyor here in a full situation. We've put the switch as far back on the non-pressure side as possible. Why is this important? It allows us to fully utilize the mass conveyor before we shut it down on full population. The other thing that's important here is to have your conveyor company design a switch that's self-clearing so that there are no bottles left in the inset of the bottle switch. So make sure that you can completely fill up that conveyor.
So the next area we want to talk about a little bit is accumulation. On this drawing, we've showed an inline accumulator and a bidirectional accumulator. They can pretty much be used interchangeably, but it should be noted that the inline accumulator is a little more first in, first out. It's not guaranteed, but it's more first in, first out than a bidirectional table. A bidirectional table guarantees you that you have first in, last out. The important thing is to have the accumulation on the line so that you can store between operations. And you got to remember that any area that has containers in it during normal transition is not accumulation. You can't count that as part of what you're getting when you accumulate because that area is already full. We've shown a bidirectional table here with the nested accumulation on it. And one of the questions we get a lot of is how do we calculate nested accumulation on an accumulator? Let's go to the chalkboard and take a look. Here's the technical formula. You take the number of inches in a foot, you divide it by the container diameter in inches, and you square that number. That would give you the number of containers unnested in a square foot. You take that number, you divide it by the cosine of 30 degrees, which is 0.866, and that gives you the number of round containers per square foot. Here's the actual calculations. Let's say we've got a 3-inch diameter container. You take 12, you divide it by 3 and you square it, you'll get 16. Then you take the 16, divide it by 0.866. This gives you approximately 18.5 round containers in a square foot. You know, one of the areas that we see often in factories that isn't correct is the guide rail settings. It's especially important when you have a mass conveyor with round containers that you maintain the nested pattern and not let the pressure created by the nested pattern press out onto the outside guide rails. It causes issues with the flow, it causes issues with maintaining the nest, and then when you get to where you're using the containers aren't where you think they should be. So we like to go through and calculate the dimensions that need to be set for the guide rails to get them properly set up. So the calculations for setting up your guide rail dimension is kind of a two-formula system. First, you determine how many containers you can get across the chain, and that's what this formula shows. C is your chain width, D is your container diameter. So you take the chain width, you subtract your container diameter, and that's because you don't have a nested pattern along the outside rails. Then you divide that number by the container diameter times 0.866. That gives you the distance in a nested pattern, and you add back 1. This gives you a number that is the maximum number of containers you could put across that conveyor width. You round that to an even number, and you move to the next formula. So you take your x, you subtract 1, again, that's that container diameter along the rails, times the container diameter times 0.866. You add back that outside container diameter, and then you add a 1/16 of an inch for clearance, and that'll give you your guide rail setting. I know it sounds a little complicated. Let's run through it with some actual numbers. So we're going to start out with a 15-inch wide mat top chain and a 2 3/4 inch container. You take 15, which is the chain width. You subtract that container diameter, 2.75. You divide by 2.75 times 0.866, and you add 1. And that gives you 6.14. Now in this case, we're going to round down. If you wanted your containers to hang over the chain on the outside edges, you could round up, but we'll round it down to 6. In the second half of the formula, we're going to take the 6 and subtract 1 times the diameter, 2.75, times 0.866 plus 2.75 plus a 1/16, and that gives us 14.72. I'd probably round that to 14 3/4, but that would give you the ideal setting for this container diameter on this chain. It would keep the pressure off of the side rails as much as possible and maintain the pattern through the entire guide rail.
Continuing down the line, what we want to do now is just focus on the packer infeed area. Here we show a multi-packer and a drop case packer like you might see in a line of this nature. What you will see is a division between the multi-packer infeed and the case packer infeed. By doing this, we're able to set up our guide rails for the multi-packer, our dividing and combining, in order that we can set the pattern, leave the guides, and have maximum setup for those operations. One of the things I've always believed in during my career is the fact that combiners should combine, dividers should divide, and accumulators should accumulate. And by segregating these operations, we can get the absolute maximum efficiency for these two setups. The next part of our presentation, we will look at environmental concerns. Beyond the line design, it's very important to look at how we can access equipment for maintenance, raw materials, and for servicing. On this initial equipment layout, we see personnel aisles dotted in. And if you look at this closely, you'll see this is an open-ended system which allows personnel access to all of the equipment without the need to go under or over any conveyors. There are no crossovers, stairways, etc., to prohibit accessing the equipment. This is essential, we believe, for personnel safety and for accessibility for maintenance personnel. The next one we see here in this particular layout overviews the fork truck traffic aisles. And it's essential here that all of the fork truck and material flows are not blocked by equipment as well, so that the fork trucks can bring equipment and consumables up into the area that it needs to be, and also we can remove dunnage. One of the things we hear so often, Jim, is the fact that while we've allowed access for material, we did not allow access for dunnage removal, and the area gets very congested and unsafe for operators to work. Jim, we've talked about a lot of things today, but what do you think the major takeaways are from today's presentation?
One big one is that you can enhance your standard components for optimal operation. The second is that you ought to run the math with your conveyor supplier engineering company to maximize the line control and accumulation. How about you?
We also talked about increasing the personnel and fork truck accessibility for operator access, for consumable access, and just general accessibility to the line. And as you pointed out in the first part of the presentation, the VCurve calculation is essential to design the line in the proper fashion from the very beginning. And also, if you're buying new equipment, you should always recalculate your VCurve to make sure you're picking out the right piece of equipment. Well, we hope you've learned something today.
You know, Power Engineers is always available to help people and give advice on packaging systems. Please feel free to contact us. We'd love to hear from you.